we now come to one of the most important topic in probability theory, expected value. What are the payoffs in a game of chance if you make a habit of playing that game? So a game of chance, like the lottery, each time you buy a lottery ticket you might win or you might lose, and it's not determined what will happen. But what is perhaps determined is what's the situation over a long time. If you make a habit of buying a lottery ticket every day, what would that be? So let's say, suppose that the payoffs in a particular game of chance are distributed according to the random variable x, and those payoffs are x1, x2, xk. Those are the payoffs that occur with non-zero probability. Those are the corresponding probabilities. So suppose we decided to play n such games. What would be the average winning, the average payoff per game? So let's see. Suppose we play those n games and then we record. Let's say n of x1 is the number of times out of the n games that we won payoff x1. So this is the payoff of some of those games. Suppose that we won x2 this number of times, and all the way until we won xk this number of times, where this signifies the number of games out of n games total that this payoff came up. And we divide by n. That would be the average. That's how many times we added x1. This is how many times we added x2, and all the way to the number of times we added xk. We group it like this, divide by n. And let's now see what this average approaches when we push n to infinity. So what happens as we push n to infinity, observe this number here is the running frequency. If those winnings have a probability of occurring, then you expect the number of times we get a success, that is when we get payoff xj, divided by total number of trials to approach the respective probability of xj. So in the limit we get this number. So having seen that limit, we come to a definition. Let x be a discrete random variable that takes on the values x1, x2, x3, so on. The expected value is simply defined to be the sum where we multiply each of the possible outcomes of x, plus each of the payoffs, by the probability of those payoffs happening. And that is this infinite sum. And it can be written in this form. It's the sum that goes over all x, all real number x, where the probability of that x is bigger than 0. So we sum x times p of x. We have seen that when x is finite, the expected value represents a weighted average of x. Let's see how that might work. So find first the expected value of x, where x is the outcome when we roll a fair die. What happens when we roll a fair die? The possibilities are that we get 1, or 2, or 3, or 4, or 5, or 6, and each with probability 1 over 6. So we see that it's the expected value, which is then simply the sum k equal 1 through 6 of k multiplied by 1 over 6. Because the probability that I get outcome k is 1 over 6 for each k. And what do we get? This is simply 1 over 6 times the sum. You remember that the sum can be written as 6 times 7 divided by 2. So it's 1 over 6 multiplied, so it's this 1 over 6, multiplied by the sum, and this sum is nothing more than 6 multiplied by 7 and divided by 2. loose, we can simplify it and simply write 7 divided by 2. So what does the number 7 over 2 mean? Imagine you run a very long simulation and you see the individual outcomes. Sometimes the die came up to be 1, sometimes 3, sometimes 7, 8, sometimes 6, 5, 3, whatnot, right? It goes through a bunch of numbers, and then you look at those numbers and you average those numbers out. So you play 10 games, you average those numbers out. You will see that the average will tend more and more to look like 7 over 2. Here is another example. Suppose that you have a fair die and you win $6 if that fair die comes up 6, and you lose $1 if the die comes with any other number. Would you like to play this game? So let's suppose that y is our payoff. And what's the expected value of y? The expected value of y is simply I get $6, and the probability I get $6 is 1 over 6. And I lose $1, which I can write as minus 1. And the probability I lose the dollar is 5 over 6. So I get that the expected value is 1 over 6. It means that if I played many games, I will find the more games I play, the more the situation looks like each game I earned a sixth of a dollar. So you see, when I play this game, truly I sometimes gain $6, sometimes I lose $1. But if I play many games, the overall outcome would have been the same as if for each game I was paid a sixth of a dollar. So you can see that if I could perform many of those games very quickly, you will gain roughly 1/6 times the number of the games played. So if you play, say, 1,000,000 games, you might think you will get 1,000,000 divided by 6. Right? If of course you can play the game very rapidly, this would be a very good deal. So it's often interesting to see when the expected value is positive when it relates to payoffs in games of chance. Expected value positive means that perhaps the player, or whoever it's positive for, has an advantage in this game. And that would result that over a long period of time, over many games, it will be as if the same definite determined score is given to the player who possesses that positive expected value. Has anyone seen the movie The Deer Hunter? In that movie, Christopher Walken and a few other people playing American POWs are captured by the Viet Cong, and while prisoners, they are forced to play a game of Russian roulette. So in that game, one is given a pistol, and let's say the pistol has 7 chambers. You put a bullet in one chamber, you roll the drum, you press the pistol against the tempo, and you fire. So the Viet Cong, they would bet on the person to survive. So how many games, how many rounds do you think a typical Russian roulette game will last? Let's suppose that x equal 1, 2, 3 equal to a positive integer represents the number of rounds. Then the probability that the game lasts for n rounds is the same as the probability that in the first n-1 rounds the bullet is not fired, and on the very last nth round the bullet is fired. So by independence, each round, each game has a probability of 6 over 7 that the bullet is not in the chamber fired. So 6 over 7 to the power of n-1 is the probability there is no firing of the bullet for the first n-1 rounds. n times 1 over n. That's the probability the bullet is fired on the last round. The expected value is then this infinite series, n times 6 over 7 to the power of n minus 1 times 1 over 7. Pow pow, as the Vietnamese say. So we can do all this calculation as we are going to, but would you think for a moment and try to see if you see the expected value ahead of time? What is the number? Think about it. So sometimes the game is over in 1 round, sometimes in 2, in 3, could be a long many rounds. But what do you expect to be on average? How likely is a person to select a bullet? A person has probability 1 over 7 of selecting the bullet. So you expect that on average, 1 out of every 7 times we fire the gun, that will dislodge the bullet. Therefore, we can predict, even without many calculations, we can expect this number to equal 7. On average, we would think that the game lasts exactly 7 rounds on average. So let's try to figure the sum using just logic. So recall how we can sum geometric series. So this is not exactly a geometric series because there is an n in front of it, but we'll get there. So first, if I have a geometric series, it's, let's say, of the form 1 plus x squared onwards, we can see that within the sum, I can figure out, let's say, by looking at x squared and onwards, I can just factor out the x as I do in here, and I see that whatever is in the yellow parentheses is that same value of the geometric series g. So I have that g equals to 1 plus x times g, which immediately gives me that 1 minus x times g is 1, which means g is 1 over 1 minus x. Now, how do I figure sums that look almost geometric, but they have this n in front, right? What do I do now? So I can try to use a similar idea as we did before. I parcel it out. We have n minus 1 times x to the n minus 1 plus x to the n minus 1. You see, here I just took an isolated x to the n minus 1. So then I can distribute the sum. I already know how to sum the second part. This is just a geometric series. So now how do I sum this part? Well, I can relabel and say that n minus 1 equals to m. So we have a summation from m equals 0 to infinity of m times x to the power of m plus this sum that I was able to calculate. Now, this we labeled as s. What is this? Think about it carefully. I can, if m is 0, that cancels the summation. I might as well start m at 1. Nothing is lost. I'm just not mentioning the 0 term label, because 0 times x is nothing, right? So I start the summation from 1. It now looks very much like the original sum, except here x used to be to the power of 0, and now x begins with the power of 1. So I can just factor out the x, and I see that this sum is nothing more than x times my original expression. Therefore, the original expression equals to x times the original expression plus 1 over 1 minus x. And the consequence, just solve basic algebra, you get that s equals to 1 over 1 minus x squared. So is that indeed 7? Well, let's see. We have this 1 over 7 in here. We have 1 over 7 that I factor out. Then I simply have 1 divided by 1 minus 6 over 7, the whole thing squared. What is this number? This is nothing more than 1 over 7 squared multiplied by 7. You get 1 over 7. And indeed, the answer is 7 as we expected.